So for the last learning module of this lecture, we're going to look at the visualization known as a scatter plot, and we're also going to talk about the idea of polynomial regression, and we'll actually apply this to a particular data set, and you'll get another chance to do that during your homework this week. So scatter plots are nothing more than visualizations of what are known as bivariate data. So bivariate data is just when you have a particular sample, if you just don't only have one data description, but you have two. So oftentimes these things are easier to see through examples. So imagine that you had a bunch of cars as your samples, and for each car you weighed the car and you determined its fuel economy. That would be an example of bivariate data, because for each sample of a car, you would have two different data points or two different measures. So bivariate data, usually when you have it, you assume that there's some relationship between the various variables. And if you only have bivariate data, you have two, you would assume that there may be some relationship between the two. That's probably the reason that you collected the data originally. So in the case here, we might assume that the heavier a car, the worse the fuel economy would be. Well, how can we actually quantify that? Well, maybe the easiest way to do it is just to create a plot that shows how, when the weight of the car varies, the corresponding fuel economy varies. And that's exactly what a scatter plot is. So we're just going to take each sample that we have of bivariate data. We're going to pick one variable to go on the x-axis. We're going to pick one to go on the right, and on the y-axis, I should say. And usually we're going to choose that particular assignment based upon our assumption of causality. So we would assume that the weight of the car influences the fuel economy. So in that case, the car weight will go on the x-axis and the fuel economy will go on the y-axis. Now, because of the way that these type of relationships that we're usually describing with scatter plots work, it really doesn't matter if you invert the axes, you can still see the relationship. It's just harder to tell a story with it. So scatter plots are nothing more than plots of bivariate data where you have one variable on the x, one variable on the y-axis, and you take each sample of data and you just make a plot. And what can you do with scatter plots? Well, one thing you can do that's oftentimes used within engineering is to kind of qualify. And I'm using qualify here because it's not technically like you can actually put a number on this. You can quantify it. However, when you have this graph, you often tend to just describe a relationship between the two variables that you're plotting in some loose way. And the one that you definitely want to be familiar with is being able to recognize correlations between bivariate data. And correlations are nothing more than a linear relationships between the two variables. So if you notice on the left pane here, as x increases by a single unit, the general increase in y tends to stay the same whether we're at the lower values of x or the upper values of x. This looks like a linear relationship. So it appears that x and y, not perfectly, but tend to follow some type of linear trend. So we would say that x and y in this case are positively correlated because as x increases, y increases in a linear type fashion. In a similar logic here in the middle pane, these two variables would be negatively correlated. And notice again, you don't have to say linear correlation because correlation implies a linear relationship between the two variables. In the right pane, notice that we really don't have any relationship between x and y here, right? These tend to exhibit no correlation between the two. So as I mentioned earlier, you can kind of just describe those visual relationships based upon what you see, but you can also quantify this. In the case of correlation, you can compute a correlation coefficient, but what I'd prefer to talk to you about today is the idea of polynomial regression. And regression in general is the idea that when you have bivariate data, you can build some kind of predictive model that allows you to estimate the value of the dependent variable given the value of the independent variable. So that's just to say you build a model such that if you give it an x value, it predicts what the y value should be. And there's lots of different functions that you can use in order to make that approximation. This is actually a very, very emerging field of research. You can use neural networks if you're working in kind of supervised learning within artificial intelligence, but the most simple form of function that you can use is a polynomial. And a polynomial, we all remember, is just a bunch of numbers, which are the coefficients here denoted by a0, a1, and a2, and variable terms that are just the variable raised to a power. So here the variable is raised to the 0th power, first power, second power, all the way up to the nth power. And in general, whatever the largest power is, we call that the order of the polynomial. So here we have an nth order polynomial. What happens is we can choose, so think it's a little bit easier to think about in the case of a first order polynomial. So if we had a first order polynomial, we just have a line. And remember, we can always draw a line to go exactly through two data points. However, in general, once we get above two data points, if those points aren't on the same line, the line won't intersect each point perfectly. However, it's pretty intuitive that we can draw what's known as a best fit line, right? I can draw a line in the middle here. And if you were trying to draw a best fit line, what would you do? You'd probably choose your line, the two parameters, a0 and a1, such that the distance between your line and the data points, if you squared them, that distance would be minimized. clearly a line that went like this would be better than a line that didn't even intersect any of the data at all. And that's actually how this algorithm works. And we'll look at this a little bit later when we get into the numerical methods portion of the class. But the way the parameters, and in this case, the parameters are the A0, A1, and so on values of the polynomial, are determined is by minimizing the square of these residuals. That's how those values are determined. But the important thing is we can actually do that relatively easy in Excel, and we'll look at a model here in a minute. And polynomial regression can be used for a lot of different things. It can be used for prediction of data that you don't have available. In general, data is very expensive in order to get. So if you only have a limited amount, you might want to predict values of the dependent variable for combinations of the independent variable that you don't have. In addition, if you have noisy measurements, you can actually use it in order to make an estimate of a parameter of the function that you're attempting to measure. And that sounds a little bit confusing, but I'll show you how to do it here in a minute. So I give you another spreadsheet called displacement force data within the files, the sample data files within the course website. And what I'd like you to do is generate a scatter plot of the force displacement data for a spring 1 in Excel, and then fit a linear regression model and show the model and coefficient of determination on the graph. And I haven't even told you what coefficient of determination is yet, but a lot of times when we teach these kind of advanced subjects, I like to just do an example and kind of go from there. So I'm going to download the spreadsheet. I'm going to pull it up. And what do we notice here? Well, remember that for a spring, right, naturally when you stretch a spring, that's known as the displacement. The restoring force is just a measure of how much it wants to pull back. So the more that you stretch it, the more that it wants to pull back. And if you remember back to your physics course, those two are linearly related. Particularly the restoring force is proportional to the displacement, where K is the spring constant, X is the displacement, and F is the restoring force. So we were told to kind of generate this curve for spring 1. So I would want the displacement values on the x-axis and the restoring forces for spring 1 on the y-axis. So the way I can generate a scatter plot in Excel is just to highlight that data, go to the Insert tab, and then Scatter Plot is all the way down here to the bottom right. And I'm just going to insert this scatter plot. And if you notice, naturally, it does a lot of smart things for me. It is automatically chosen which values should be on the x and y axis. It does that by placing whatever value is in the column to the left on the x and whatever value is in the column on the right on the y-axis. So I can add excess titles, which I'll do by clicking on the plus and then checking excess titles. On the x-axis, I will put the displacement, and this is measured in centimeters. On the y-axis, I will put the restoring force, and this is measured in newtons. And you can play around with this a little bit more. For example, there's no need to have your x-axis go down to 0. So you can right-click and go to Format Axis and change the bounds to 1 to 4, just to make a little bit of a tighter graph. But we're not focused too much on the visualization for now. What I wanted to show you is, first and foremost, does this data fit our hypothesis? We know in this case that the restoring force should be related to the displacement in a linear fashion, and it looks like it is. But the question is, how can we use linear regression or polynomial regression in general at the first order in order to quantify this? I should say. So left click on one of those data points, and you notice they all become highlighted. Then right click and go to Add Trend Line. And you notice that the first trend line that pops up is actually a linear fit. You can in general use an nth order polynomial, but we're going to focus on linear for now. So what I asked you to do is actually put the equation and the coefficient of determination on the chart. So what I didn't tell you is the coefficient of determination is actually this r squared value. And you can look at this r squared value as nothing more than a measure of goodness of fit. So if you notice, r squared in this case is 97%. If you convert it to a percent, that shows that this model, this linear model, is a pretty good fit of this data that we have. And what we see here is if we were to fit a line or a linear polynomial to it, the slope would be 1.8823, and the y-intercept would be 0.5613. Now, if you think about it, in this case, we know a little bit more information. We know that the underlying physics of this model say that we shouldn't even have a y-intercept. So if you go back to that trend line that you fit here, you'll actually notice that one of your options is to set the intercept to 0. And in that case, what you're doing is physically telling the model, hey, I know the y-intercept should be 0. And notice what happens to the coefficient of determination there. When I didn't provide that information to the model, it only did a 97% job of fitting this data. However, when I set the intercept to 0, it has 99.4% coefficient of determination. It does a much better fit. So if you notice in this case, what we're really doing is we're coming up with a way, assuming that these measurements are noisy, to estimate the spring constant. So based upon the fitting of a linear function to this data, right, we know that in general, the restoring force is proportional to the displacement, and that constant of proportionality, or the slope, is the spring constant. So for spring 1, it appears that the spring constant is basically 2.0694. And what would be the units? Well, if x is in centimeters and we need to get something in newtons, that would be in units of newtons per centimeter. So what we would say in this case is that K estimate, or the best case estimate of the spring constant, is 2.0694 newtons per centimeter. And on the homework, I'm going to have you repeat that for spring 2 and spring 3. So hopefully this gave you a good introduction of how Excel can be used for actually fitting data using polynomial regression, and what the underlying meaning and use of a scatter plot is.